Hi everyone, welcome to the week 5 of this Sobolev Spaces and partial differential TA tutorial. So, in this week, in the video lectures, we have studied about the this Sobolev spaces, and we dwell deeper into the Sobolev spaces and got to know about this properties of Sobolev spaces and realize that we have this CC density, which is a we always have there in LP spaces. It's not exactly here in this Sobolev spaces, but once we have this sort of extension stuff kind of stuff, so we also saw that we cannot extend any like in the case of LP function, we can directly extend the LP functions. Here we cannot directly extend our Sobolev functions directly to the whole space Rn. So we require some properties of our boundaries or behavior of the function sometimes to extend in the to the whole of the domain. And so we saw some extension theorems regarding that, and also we had some once the extension theorems are there, we had finally saw this Poincare inequality. So this Poincare inequality tells a relation between this the LP norm and the Sobolev norm, and eventually it gives the byproduct of this Poincare inequality is that we ultimately on this Sobolev spaces in basically W naught 1p spaces we have an equivalent norm instead of the normal norm, and that norm is just considering the gradient term only, and that is actually quite helpful when we basically consider this type of problems that involve Laplacian or pre-Laplacian kind of things, and that PD will be quite helpful when we solve that things because we only have to work on just particular that type of half norms only, and that quite helpful. So without further ado, let us have a start of a tutorial for this week. So the first question is like in LP spaces, we have see this type of containment in the LP spaces that if my P is less than Q, then LQ is contained in LP, provided my measure of my domain is finite. So um, that type of thing is actually um, we saw in LP spaces, but we saw one more thing that uh, when we remove this condition of domain to be unbounded, we have like no containment, like no side containment. So, but since now we are adding this domain, this now derivative condition to be integrable, pth integrable, we would like to, we expect that there may have chance of containment even if my domain is whole of R, but that is not the case in Sobolev space as well, as we see from this problem, that even when I have the full domain R, we have basically no side containment is there. So we do have some type of functions that exist, and this actually ultimately gives to the same result as we have in the LP spaces. So let me write the question. So consider the function ux equal to 1 plus x square raised to power of minus alpha by 2 into multiplied by log of 2 plus x square whole inverse, and x belongs to real numbers, and my alpha x belong from 0 to 1. We have to check that using the Sobolev space W1P for all P in 1 by alpha to infinity and that U is does not belongs to LQ R for all Q in 1 to 1 by alpha. So this function is actually differentiable everywhere. So the classical derivative, the weak derivative coincides with the classical derivative. So all we have to check is the integrability of the function and its derivative only. So first of all, let us check the integrability of a function. So I have to check the pth integrability. So I considered all r mod ux raised to power of p dx. So this is what? This is nothing but, since our function is even, so this is nothing but twice of 0 to infinity 1 upon 1 plus x square raised to power of p alpha by 2 and 1 upon log of 2 plus x square whole raised to power of p dx. Moreover, we can note that as limit x tending to 0 1 upon 1 plus x square p alpha by 2. So ultimately I need this integral to be finite. So it's better to calculate the integrability of this function. You have to check the since this function is not so easy to evaluate, we have to see some easier version of integrals which have the same convergence property as this integral. So to do that, first of all, let us evaluate the limit at x tending to 0 into log 2 plus x square whole to the power of p. So this limit is nothing but 1 upon 1 into 1 upon log 2 raised to the power of p. And this is actually a finite number, which is finite. So this implies the limit exists. So the integral in one converges if and only if the following integral converges. Now what is the integral? The integral is integration 1 to infinity 1 upon 1 plus x square p alpha by 2 upon 1 upon log of 2 plus x square whole is power of p dx. So so it's enough to evaluate the convergence property of this integral. Now to evaluate this integral, let us have a change of variable. So we can assume this log of 2 plus x square to be t, then 1 upon 2 plus x square 2x dx will be equal to dt. Moreover, this will imply that x has to be et minus 2, and then we have to take the square root. Since x is I'm taking to be in the positive only, so I have to consider only the positive square root. So our I1 is nothing but I is from log 3 to infinity. And what is this? This is 1 upon et minus 1 whole power of p alpha by 2, and this whole becomes 1 upon t raised power of p, and all the remaining things turns out to be half et minus 2, and this whole thing becomes e raised power of t dt. Now next what we would like to see that one thing we have see that there is exponential in the denominator, and since we have to only see the behavior at infinity only, so if we have by any chance uh, the exponential to have a positive power, then we may be in trouble, and this integral will definitely not be finite. So the first thing which we like to have is that this I is integrable. I is one thing I know is not integrable. Sorry, is not integrable if power exponential. So more or less again it's not integrable if limit as t tending to infinity e t e t minus 1 p alpha by 2 e t minus 2 is non-zero. And this is happening because this is an integrable and continuous function, and we know that one thing, if we have an integrable continuous function, then its limit has to be go to 0 as x tends to infinity. Oh yeah, so this will be a square. This will be half power here because I just consider twice of x only. So it's half here, and this is t by 2. So this is equivalent to this thing. And what is this limit? This is nothing but the limit as t tending towards infinity. E t 1 minus p alpha by 2 minus half, and this is non-zero if and only the power to be 1 minus p alpha by 2 minus half to be non-negative, so it's like greater than or equal to 0. So once that's the case, we have this thing half less than or equal to p alpha by 2, and ultimately this implies p has to be less than or equal to 1 upon alpha, 1 less than 1 by equal to alpha. So ultimately, there's one more thing, that this t raised power p is also there. So you have to consider t raised power p here as well. So again, your t raised power p here, and again your t raised power p here. And to have this, we ultimately need this borderline case. So this has to be greater than 0. Ultimately, this gives that half is less than p alpha, and ultimately this gives that p has to be so this is the way around. So p has to be less whenever p is less than 1 by alpha. We know that this integral is not at all integrable. We have to check the case whenever p is equal to 1 by alpha. So that case is we still need to consider. Or whenever it's 1 by alpha or greater than 1 by alpha. So at least one thing we know for sure, that is it is not integrable if that is not equal to 0. And so now you have to check the remaining cases. You have to check the integrability at the remaining cases. So case when my p is exactly equal to 1 by alpha. Then our integral actually turns out to be I is equal to log 3 to infinity e raised to power of t whole divided by e raised to power of t minus 1 power half t raised to power of 1 by alpha. And note that alpha is between 0 and 1, so p has to be greater than 1. And finally, this is et minus 2 power half. And this integral is equivalent to I1, which is nothing but something like log 3 to infinity. So et has same, more or less same power, and basically that limit converges to 1 only. This is the same convergence property as t 1 by alpha only, and we know which is finite as 1 by alpha is greater than 1. So this is integrable. So ultimately we have this u to be integrable whenever my p is equal to 1 by alpha. We still have to check the derivative to be integrable, but let us check the other cases as well. The other case, when my p is greater than 1 by alpha. Then ultimately our integral will have actually an exponential factor, and that exponential factor is actually negative. So I is actually log 3 to infinity e et minus 1 raised to power of tp alpha by 2 raised to power of p and e raised to power of p minus 2 whole divided by half and dt. So again, as we can notice that P is greater than 1 by alpha, and alpha is actually greater than 1, greater than, like alpha is lying between 0 and 1, so 1 by alpha is greater than 1. So ultimately, this integral is dominated because is dominated by some constant time log 3 infinity 1 upon t raised power of p dt, which is finite since the limit of et as t tending to infinity et minus 1 tp alpha by 2 et minus 2 half this whole thing since p is greater than 1 by alpha, the whole power will be a negative power of an exponential is actually 0 only. Since that is the case, so we have this upper bound of constant, and this will give a integrability properties over Sobolev function. So next we would like to finally see that since this function is actually integrable, now finally I have to check its derivative to be in pth integrable for this range whenever my p is greater than or equal to 1 by alpha. And that is also not so hard to see. So let us do that as well. So if ux is this 1 upon 1 plus x square is power of alpha by 2, 1 upon log 2 plus x square, then u dash x is so we have to evaluate this limit. So we can use this product rule. So this u dash x will be minus alpha by 2, 1 plus x square, alpha plus 2 whole divided by 2, and then we have a 2x solved log 2 plus x square plus 1 upon 1 plus x square whole divided by alpha by 2, and then we have to differentiate this thing. So this is minus 1 upon 2 plus x square into 2x whole divided by log 2 plus x square whole square. So this is equal to minus half of alpha x 1 plus x square alpha plus 2 whole divided by 2 into log of 2 plus x square, and then we have minus 2x, and then we have this 1 plus x square alpha by 2, 2 plus x square log of 2 plus x square and whole square. So one thing is clear for sure, that this is again a bounded function, because at then I have this alpha is between 0 and 1. So it's like the first term we have x, and then in the numerator and the denominator it's 1 plus alpha by 2. So alpha by 2 is giving something more than 1. So this whole thing actually is bounded. So actually this proving that u is in 1p clearly. U belongs to W1 comma infinity R. So this is very trivial to check because of the powers involved. So next, what we would like to do, we would like to have this integrative property. So we need to see that this u dash x is integrable. And how do we do that? We can individually show that these two integrals to be finite. And one can check these integrative properties individually. So it's like the same analysis as we did for the integrable. So one can check that u dash x belongs to L Q of R for Q in 1 by alpha comma infinity, alpha to infinity. So this is can be checked as using the same ideas to check ideas that was used to check uh, U to be integrable. So like the same idea. So it again prove the fact that what we see for the LP function, same sort of thing we have in for the Sobolev functions. So next, what we would like to see, we would like to see this behavior like basically a would say a compactness behavior whenever we have a Sobolev function. So that Sobolev function ultimately give rise to a similar. So if you have bounded sequence in Sobolev space, ultimately that gives rise to a convergence of sequence in some LP spaces. So that it's more like a compact embedding, which we would see, but in a more general environment. But we will see some glimpses of that in this next question. So, and these things are heavily used when we try to solve the partial differential equation using these function analysis tools. So let me add the question. So let I be equal to the open interval 0, 1. Assume that un is a bounded sequence in W1PI with P lying between statistically greater than 1 and less than equal to infinity. Show that there exists a subsequence UNK and some U in Sobolev space W1PI such that UNK minus U, the infinity norm goes to 0. Moreover, UNK dash converges weakly in LP I for 1 less than p less than infinity, and u and k dash converges weak star to u dash in basically the converges weak star in L infinity I. So that's the first part. So again, it's sort of compactness. We have a bounded sequence and ultimately getting a convergence subsequence, as you see in various uh, in various parts of analysis. So how do you go about showing that such subsequence exists? So one thing we know that we know that W1P functions are actually absolutely continuous. So these one thing we know that U and X that for any n we have this U and X minus U and Y whole thing equal to integral y to x U n dash t dt. So this is the integrable. So this is the our weak derivative, but this is integrable in fact because since we have a finite measure, we can write this thing because ultimately we use Helder to finally show that this integral is finite always. So how do we go about? We can use using Helder inequality. We have mod u and x minus u and y mod. This is using Helder y to x mod un dash t dt plus of p whole is power of 1 by p times mod of x minus y whole is power 1 by q, where 1 by p plus 1 by q is 1 only. This is the Helder inequality. So using that, we have this thing. And so this actually, so we want to show the convergence subsequence in the array infinity norm. So it's like having, since these functions are absolutely continuous, so it's like using a compactness argument for continuous functions. And we know that one theorem that helps us to get a convergence subsequence is that Arzelà-Ascoli theorem. So with this, we have this thing that since un is bounded in W1P, so this thing is actually bound over some uniform constant times mod of x minus y whole is power of 1 by q. And that holds for all x, y in 0, 1. And what this gives us? This gives us equicontinuity. Moreover, since W1P I0 functions are absolutely continuous, in particular, they are uniformly continuous, we can extend each un uniquely to this closed interval 0, 1. So we can have a compact domain. So finally, we have a compact domain and a sequence of equicontinuous functions. All we need to show that they are uniformly bounded. So to show that uniformly bounded, we first have to prove one thing, that next we claim that this now un0, the sequence I'm getting, this thing is actually is bounded. So if not, there exists a subsequence unk of un which is not bounded. So if that's the case, what can we actually prove is that if that is not the case, we think one more thing which we can observe is that, moreover, un if un, which is the function un only, so if un achieves minimum at small m n and maximum at capital Mn, then mod of un minus un small mn. So this is actually a positive quantity only. This is less than equal to the m times mod of mn minus small mn. And this is again less than equal to m because mn and small mn are actually lying in my open interval 0 and only. So ultimately the difference is uniformly it's actually uniformly bounded for each function un. So now since this unk are not bounded, what now we can have here is that this actually implies that un mn minus un small mn is equal to capital M. Finally, what do we have here is that for the un0 it will be, which is not bounded. So what can I write is un 0 minus un un mn. This thing is less than equal to un capital Mn minus un mn. And all of this is actually less than equal to some bounded constant m only. And what else we do have here is, since un 0 is as un k 0 is unbounded, we can assume that un k 0 is greater than equal to k for all k in n, and ultimately this gives us that this un small mn, so the minimum point, is actually greater than equal to, greater than equal to un 0 unk, sorry, unk mnk. So it's also k here, so that's not k, but yeah, that's can be avoided. So un mnk is actually greater than equal to um so un mnk is greater than equal to m minus, so un 0 minus n 0, unk 0 minus m. So what this basically implies, this implies that the minimum value is also unbounded, and ultimately this thing is greater than equal to some k minus capital M. So once that's the case, what do we have here? We have the integration of 0 to 1 mod of unk mn unk. I know since they are in LP, so they are in L1, so this is finite, but unkx dx is greater than equal to what? This is greater than equal to 0 to 1 unk into mnk, which is the minimum value, dx, and again finally this is greater than equal to. So ultimately we can assume that this whole thing un 0 to be non-negative. Ultimately we can have that particular kind of stuff to be here, and ultimately what we are getting here is that but ultimately we can replace that by minus u, so we can assume these quantities to be um, positive. So finally this will be just greater than this is nothing but unk 0 minus m, and this is nothing but greater than equal to k minus m, and that holds for all k in n, but which is a contradiction. What this basically implies? This implies that this un 0 is bounded. Once that is the case, what we can have finally is that this unx, so this some subsequence, so unk will be bound. So ultimately that whole is bounded. So ultimately we have unx, the mod is less than equal to unx minus un 0 plus un 0. So I know the first thing is bounded and the second thing is also bounded. We have proved. So first thing is bounded by this EQ continuity argument which we have shown above. So whole thing is actually bounded by M, and this is, let's say, some m1. So this is bounded, in fact uniformly bounded, thus by the Arzela-Ascoli theorem. They exist subsequence UNK of UN such that UNK converges to U in L infinity norm for some U in W1PI. So actually we have a convergence in actually the L infinity norm, but we can go back to the convergence in the Sobolev norm because we have this uh, ultimately not the Sobolev norm. Ultimately we have this to be in W1P because this will again have the properties of a UN case, which will give me a continuity, as well as there is a, since this is a bounded sequence, so ultimately this eventually have a subsequence which is weakly convergent and have some pointwise properties, which eventually give us this some U to be in the Sobolev space as well. So that can be proved, that is not so hard. Finally, we need to show that U and K dash converges weakly to U dash in LP I for 1 less than P less than infinity. So how do we do that? So we'll let V, or let's say take W to be in LQ, which is the conjugate exponent, W in the LQ, I, where 1 by P plus 1 by Q is 1. And so to show weak convergence, we have to show basically U and K times W. So this dash is the, this converges to integral I U times W. So how we show that? This is, can just consider the integral U and K minus U times W and apply Helder inequality. This is integral I U and K minus U raised power of P whole raised power of 1 by P. And then this is integral of I mod WQ whole raised power 1 by Q. And since we have integrability in LP norm, so we have strong convergence in LP norm. So this whole thing, actually we can take the uniform norm to be outside. So ultimately, since we have a convergence in uniform norm, so we will have a unique convergence in the LP norm as well. So this thing goes to 0 as k tends to infinity, and this thing is bounded. So ultimately, we have a weak convergence. And finally, we have to show that U and K converges weak star to U in L infinity. So again, that's not so hard. So we have to show the integral U and K minus U times some W goes to 0 as K tends to infinity over all W for all W in L1I. So again, that's not so hard. We have this integral if we consider the modulus of U and K minus U times mod W. This is less than equal to the infinity norm of U and K minus U. And then this is the integration of W. I know this thing tends to 0 as K tends to infinity. And this thing is bounded. So again, the whole thing goes to 0. So we have the weak convergence, weak star convergence. So finally, we have a second question that since we are assuming that this weak convergence there, so we have shown this for P greater than 1. So we would like to see what happens when P is equal to 1 case, but as we actually unfortunately have that, since p equal to 1 is not reflexive, we don't have this type of compactness argument present in the W11 case. So the second part of this question gives that construct a bounded sequence un in W11I that admits no subsequence converging in L infinity. So to prove this, so we don't have the same analogous result whenever my p is equal to 1. For that, what we have, we consider this type of functions un(x) to be 0 whenever my x is in 0 to half, n times x minus half whenever my x lies between half to half plus 1 by n, and finally 1 when my x lies between 1 by half plus 1 by n, comma 1. So one can check the weak derivative un dash x to be equal to 0 if x lies between 0 and half, n if my x lies between half to half plus n 1 by n, and 0 again if my x belongs to 1 by half plus 1 by n, comma 1. So if we try to compute the W11 norm, we have to show that both unx is integral of unx is finite as well as unx dash. So this is nothing but half to half plus 1 by n of n times x minus half, and then half plus 1 by n to 1 of 1 only. So this will gives you n times x square by 2 minus x by 2, then half plus 1 by n into half, and this is nothing but 1 minus half minus 1 by n. This is n times n by 2 times x square minus x. So this is 1 by 2 plus 1 by n square minus 1 by 2 plus 1 by n whole thing minus 1 by 8 minus 1 by 4 plus half minus 1 by n. So ultimately this thing is finite only. So we have this thing to be finite only, and if we would like to evaluate this, we can also do that. And also, since we have to show it this to be uniformly bounded, so let us evaluate it properly so that we know that what exactly we're getting. N by 2, 1 by 4 plus 1 by n square plus 1 by n minus half minus 1 by n, and this will be plus 1 by 8, and then this is half minus 1 by n. 1 by n and 1 by n will cancel out, and this whole thing will give you n by 2 minus 1 by 8 plus 1 upon n square plus half minus 1 by n. So again, that is uniformly bounded. And if you consider the un dash x, the L1 norm of this, so this is nothing but half to half plus 1 by n and n only. So this will actually will give you 1 only, and which is again uniformly bounded. So this gives un to be uniformly bounded. But if we evaluate the pointwise limit of but unx converges to pointwise to ux, where ux is how it's defined, it is just given as 0 when my x belongs to 0 to half, and again 0 when x belongs to half to 1. So it's just sorry, it goes to 1 only. So if there exists some u and k such that u and k converges to u in L infinity I, then as u and k are continuous, this implies u has to be continuous, but this is a contradiction. So we don't have any. So this proves our what we would like to do is that we have seen that the whenever we have a bounded sequence in W and B, what we are actually ending up having a weak convergence in the LP spaces or weak star convergence in the L star L infinity space. So next we would like to see that whether the next convergence from stronger than the weak convergence, the strong convergence or the convergence, the norm topology. So we would like to see whether if we have a bounded sequence in the Sobolev space W1PR, do we have a subsequence of that particular sequence which has a which converges strongly to some element in that LP space? So actually that answer is not affirmative. We don't have in always converging subsequence in strongly converging subsequence in the LQ space, and this can be seen with this with the help of our next question. So our next question is we fix a function phi in CC infinity R and phi is identically not equal to 0, and we set what un equal to phi of x plus n. Let e be any number between 1 to infinity. First is check that un is bounded in W1PR. So that's our first step, which you would like to show that this sequence is actually a bounded sequence. To do that, we start with just calculating the just W1P norm of the UN. First, we consider the P norm. This is just whole R, and UNX is nothing but pi of x plus n whole power P. And now this can be actually written as, if you use the transformation x plus n is equal to some y, this will give dx equal to dy, and our integral is equal to again since R is translation invariant, this transformation will again on the same region R, and but this is now phi by p dy, which is the p norm of phi. Moreover, if you consider the p norm of the gradient, so this is nothing but phi of gradient of phi of x plus n and the whole power p. Again with the same change of variable, we again land up with the same equality that this integral will again equal to whole integral r of gradient of phi at x, sorry, phi at y, plus power p dy, and this is nothing but the L2 norm of gradient of phi. What this basically implies, this the W 1p norm of UN is actually nothing but the W1p norm of phi, which is not only finite but as well as which is uniformly bounded. And that is what we wanted to prove. So that's then in the next thing which we want to prove, that is that prove that there exists no subsequence U and K converging strongly in LQR for any Q in 1 to infinity, lying between 1 to infinity. So first of all, whenever we see the strong convergence, the first thing which you would like to see is that the point was limit over sequence of functions. So first of all, let us see what is, since our u and x is phi of x plus n, and also we know that phi is a CC infinity function, CC uh, infinity function. So this has a compact support. This implies that u and x converges to 0 as n tending to infinity, since phi has a compact support in R. So since this is a compact support in R, so and this holds for any x in R. So ultimately this sequence converges pointwise to 0 only. So, on contrary, if there exists some subsequence u and k such that u and k converges to strongly to u in L QR for some u in LQR only, then we know that u and kx actually converges to ux pointwise almost everywhere in R. But we know that u and x converges to 0 pointwise. So pointwise in R. So what this implies? This implies that thus u has to be equal to 0, ux equal to 0 almost everywhere in R. So this is 0 almost everywhere in R. So what this implies, but since we know that u and x converges to u in LQR, this implies that the mod of u and x u and k minus u, that q norm goes to 0 as k tends to infinity. But u is 0 only, so this just implies that u and k power q goes to 0 as k tends to infinity. But what is u and k? This is nothing but, as we have computed earlier, this is nothing but the q norm of phi only, and which goes to 0 as k tends to infinity, implies that this whole integral of phi is of q has to be 0, which implies phi has to be equal to 0 almost everywhere. But phi is continuous, so that will imply phi has to be identically equal to 0 since phi is continuous. This is a this is a contradiction. So since this doesn't hold, this implies we don't have any subsequence which converts strongly to LQR. So we don't have the strong convergence if we have a bound sequence in Sobolev space. The next thing which we would like to know about these Sobolev spaces, that we have seen that these embeddings are there. Like we will see that embeddings are there, but one thing more which we can see is that if we have a Sobolev function, then we can say one thing, that if we associate some weight with that u, then that function u will lie in the uh, LP space. So this is something stronger than the Poincare inequality. Poincare is if u is in Sobolev space, then we can say that u is in the corresponding LP space, but not only that, not stronger than Poincare. So it's like then not only lying come from the definition only, but we can also have a bound of u, the integral of the p norm of u in terms of the gradient norm, and more or less one that kind of thing is there with we have a weight associated with my function u. So let me try to answer the question first, and then we will see what's the weight I'm talking about. So the first part is that let u to be in the Sobolev space W1P with p lying between 1 to infinity. Then show that ux whole divided by x, this thing lies in LP 01. So to show this, so what we can do basically, we can so like there are many ways to prove this. So we since first of all, since we are taking u to be in the W01P space, we know that CC infinity is of 01 is dense in this space because that's the definition. So we can start with that. We can start that u belongs to the CC infinity of 01 space. So we can take you start u from this space only, and then that ux minus, so ux is equal to ux minus u0, and this thing actually, since these are absolutely continuous functions, so I can write this as integration from 0 to x u dash t dt. And then what we can do, we can have this thing that we can use the Halder inequality. So mod ux will be less than equal to 0 to x mod u dash t whole power p dt whole power 1 by p into the mod x raised to power 1 by q, where 1 by p plus 1 by q equal to 1s, and this is what we are getting using Halder's inequality. Next, what we would like to do, we want this power of ux whole divided by mod x to be less than equal to And we also can take the whole power p as well. So this will integration from 0 to 1 mod u dash t is power of p dt. And then we know that mod x has a bound 1, so we can use just directly the bound 1 here. And then what we can do is we just integrate whole from 0 to 1 mod ux by x whole power p dx is less than equal to, since this is just a constant, so it's like the 0 to 1 mod u dash t whole power p dt. And then we can use the we can take the 1 by p power both on both sides. So ultimately we get the ux by whole x, the LP norm has to be less than equal to the so this norm has to be less than the p norm of the u dash. So this proves our assertion. One more thing which we can prove from this is the second thing. Assume that u belongs to in the Sobolev space W1P with 1 less than p less than infinity, and that ux whole divided by x belongs to LP01. Show that u0 is equal to 0. So we can show that whenever there's a singularity, so if we do, because ux divided by x has a singularity at x equal to 0, so to deal with that and to have this function to be integrable, we must have u to have a 0 to basically tackle the singularity. So we have to prove this. So we can prove this by contradiction. So on contrary, assume that u of 0 is non-zero, and without loss of generality, we assume that u0 has to be positive, so we can assume that. So now, since we know that this u belongs to W1P01, so what this implies? This implies this that my function u is absolutely continuous. In particular, it is continuous only. So there exists delta positive such that ux is actually greater than u0 by 2 for all mod x less than delta. So in this delta region, we have ux to be uh, throughout greater than u naught u0 by 2, which is actually positive only. Then if I consider the integration from 0 to delta of u naught by 2x dx, so this has to be less than equal to integration from 0 to delta ux whole divided by x dx. And not only that, then we can have this Held inequality. So this will be 0 to delta mod ux by x mod whole power p dx is power 1 by p into delta is power 1 by q. So this implies, which is actually finite, since ux by x belongs to LP of 0, 1. So what this implies? This implies actually 0 to delta 1 by x dx is finite, but we know this is not the case, which is a contradiction. Thus, we have u0 to be 0. And moreover, I'd like to mention one thing which I forgot, that this thing we have proved for all u in cc infinity omega, cct infinity 0, 1, but can be extended with density. We can by density and do convergence theorems. We have a result actually. We use the pointers convergence dct to pass the limit, and eventually we'll get that this inequality holds for any function u in w0 1p 0, 1. So finally, one remark that we have proved this whole things whenever my p was greater than 1. So you like to see what happens when my p is equal to 1. So when p is equal to 1, the things actually not as analogous as for the LP case. So for this, we have, if we take ux equal to 1 plus mod log x whole inverse, then we have to check that u is in w1101, u0 is 0, but ux whole divided by x is not in L101. So first of all, so let us add the solution for this. So clearly one thing is clear, u0 is 0. So that is actually in terms of limiting process, but this is very direct. And we need to see the integration of 0 to 1 ux mod ux dx to be finite, so which is nothing but 0 to 1 dx 1 plus mod log x which is actually finite, since u0 is 0 and u is continuous on closed interval 0, 1. So this is a continuous function in a closed domain. We have this integrability. Next, we have to see the what is my u dash x. So my u dash x is nothing but minus 1 upon x, and then 1 minus log x whole square. So this is actually nothing but the integration of 0 to 1 mod u dash x. Dx is nothing but 0 to 1 upon x, 1 minus log x square dx. So we take log x to be t, then we have 1 upon x dx equal to dt, and be written as, if we take t to minus t, this is dt 1 plus t whole square 0 to infinity, and then whole thing is actually minus 1 upon 1 plus t equal to infinity to 0, and this is 1 only, and it is finite. So this shows that u dash x is in L1 0 1. So thus we have ux to be in W1101. Finally, we have to consider the integration 0 to 1 ux by mod x whole mod dx, and we have to show this integral is not finite. So what integral is this? This is 0 to 1 by x times 1 minus log x dx. So again we take log x equal to t, and 1 by x dx will be equal to dt, and the limits is minus infinity to 0. We have dt, and this is 1 minus t, which is nothing but integral from 0 to infinity of 1 plus t, which is not finite. Thus, ux by x is not in L1, 0, 1. So we have a different result when my LP space is L1. So with that, we end our session of this week. Thank you.